In this lesson, we'll look at some higher index radical functions. In the previous video, we talked about radicals of nth degree, and we defined them in such a way that they have always a unique value. So as long as we take the input from the domain of the radical, for example, for event degree radical, we had to take non-negative numbers, but as long as we take an input from the domain of such a radical, the value of it is defined in a unique way. That was needed in order to treat radicals as functions. So, since our nth degree radicals are really functions, let's try to see how they look like. In the first example, we would like to look at cubic root of x. So first, let's find the domain of such function and then graph it using table of values. Okay, what could be a domain of this function f? I call it capital D with subindex f just to indicate that I refer to the above function f of x given by the formula cube root of x. Okay, let's recall what's domain. The domain of any function is a set of all values that we can replace x by and be able to evaluate this expression. So, can we take cube root of, for example, 0? Well, yes, because cube root of 0 is 0. Can we take cube root of any positive number? Yes, there is no problem with taking a cube root of any positive number. What about negative numbers? Remember, cube root of, for example, negative 8 was negative 2, because negative 2 when cubed gives us back the radicand negative 8. So that's just an example, but you can do it for any negative number. Okay, therefore the domain of this function looks like it's all real numbers. There is no problem to calculate odd degree root of any real number. So now let's try to take a few x values and evaluate the function. Well, let's take a few negative numbers, the numbers that will be easy to calculate. For example, the negative 8, the value of cube root of negative 8 turned out to be negative 2. What other number would be easy to calculate? Well, negative 1. Maybe something closer to 0, for example, negative 1/8. Maybe 0. And try to do the same numbers but positive. So 1/8, 1, and 8. Okay, so how much is cube root of negative 1? Well, it is negative 1, since negative 1 cube gives us back the radicand negative 1. Okay, so the value here is negative 1. What about cube root of negative 1/8? Oh, that's the same as cube root of negative 1, which is negative 1, over cube root of 8, which is 2. Therefore, cube root of negative 1/8 is negative 1/2. Okay, let's record this. Cube root of 0. Cube root of 0 is 0. And cube root of 1/8, I'm sure you know already, this is nearly the same as cube root of negative 1/8, except that we have a positive number, so positive 1/2. Because 1/2 cubed gives us back 1/8. Cube root of 1 is 1. And cube root of 8 is how much? Yes, it's 2, because 2 cube gives us back our 8. Okay, now let's plot all these ordered pairs of numbers. So negative 8, negative 2. This goes out of our grid, but let's erase these extra calculations here and just try to approximate. If this is negative 5, then negative 8 it's negative 6, negative 7, negative 8, approximately here. So at negative 8, the value of the function f is negative 2. So we mark a point somewhere here. Then at negative 1, the value is negative 1. At x negative 1/8, which is very close to the y-axis, the value is negative 1/2. Okay, so it looks like the curve will be pretty steep around this section. And then at 0, we pass through 0. At 1/8, we have value 1/2. And at 1, the value is 1. And finally, we have to wait until 8. So 5, 6, 7, 8 approximately here, the value reaches 2. Okay, so to get the graph, we join these points as smoothly as we can. Let's do it. Here's our curve of the cube root function. So as you see, the domain is all real numbers, and actually the range, all the values that the function can achieve, is also all real numbers, because this curve is rising and rising forever. So it's rising pretty slow, but sooner or later you can actually reach any value that you wish. Similarly to the left, it's getting lower and lower, so all the negative values will be taken as well. Okay, what else can we say about this function? Well, it's very symmetrical. It is symmetrical about the origin. The shape is the same as that shape. So here's our cube root function. Now see another example, fourth degree root of x. Again, let's think about domain of this function. Well, this time we have to be careful. Remember, we can't take even degree root of a negative number. So it's okay to have 0, and it's okay to have any positive number, but we can't evaluate, for example, fourth degree root of negative 16. Because if this will be certain number, then this number, when raised to the 4, should give us negative 16. But no matter what number you will have here, if you raise it to the 4, to the even exponent, you will end up with a positive answer, never negative 16. So such value doesn't exist. And generally, fourth degree root of any negative number does not exist. Therefore, our domain for fourth degree root is anything from 0 to infinity. Interval from 0 to infinity. All numbers that are bigger equal 0. Okay, since that's our domain, when we try to build our table of values, we can't use negative numbers. However, we should start from the first number in the domain, because that will be the starting point of your curve. The curve does not pass this point, so that's a very important point. Okay, let's start with 0. Fourth degree root of 0, obviously it's 0. And then let's choose numbers that are easy to calculate. For example, I could choose 1/16, very close to 0, because that will be easy to calculate. Fourth degree root of 1/16 is 1/2, because 1/2 to the fourth gives me 1/16. So that's 1/2. And then choose an easy number like 1. Fourth degree root of 1 is still 1. Now the next easy number to calculate would be 16. However, that will be too far on our grid. It will be really hard to see 16. So what we can do, we can choose the last number that still fits on the grid, number 5, and just estimate and use calculator, figure out how much is fourth degree root of 5 and approximate to one place value. So you take your calculator and plug in 5 to the exponent 1/4 and then round to one place value. This is approximately 1.5. Tiny bit lower than 1.5, but approximately 1.5. Okay, we can record this in a table, approximately 1.5. And now we can plot those points. 0, 0 is here. 1/16 is even closer than 1/8 before, so it's very close to the y-axis. However, at a point that is so close to 0, the value is already 1/2. So it's even steeper than the cubic root. And then at 1, you have 1. At 5 is approximately 1.5, tiny bit lower than that. And as you noticed, we don't have any values for the negative axis, so the graph will not go on this section of the grid. Okay, we need to join those points. Let's join nice and smoothly. That's our fourth degree root function. and the domain of this function starts from 0 and goes towards infinity. This is the domain of our function. The range is all positive numbers, so again from 0 to infinity, but we haven't been asked for the range, just the domain. The last example that we would like to graph is negative fourth degree root of 2 minus x. Okay, so it has something to do with fourth degree root, which lets me believe that the graph should look somehow like this curve, possibly flipped or stretched or shifted, but somehow like this, because it's still fourth degree root. But how this may look like? Well, we don't know. We actually need to investigate by filling up the table of values. However, before that, we need to look at the domain. The domain will actually help us to figure out what x should we take to evaluate. Okay, how do we find the domain? The key part here is to keep the radicand non-negative. So we should solve the following inequality. 2 minus x should be bigger equals 0 to find what kind of x's will belong to the domain. Okay, let's bring the x to the other side. That would mean that x is smaller or equal to. Therefore, we can state the domain of f. Those are all x's that are smaller or equal than 2. So on the number line, it looks like I have a 2, let's say here, and everything that goes below 2 gives me my domain. Okay, to write this in interval notation, we would have to start from the left and go until 2. So from minus infinity until 2 with 2. That will be the last point that the function can be evaluated at. So it's the last point of the graph. Okay, therefore 2 is very important point and we should include this in our table of values. So if x is 2, let's plug it into the function f of 2. Let's use the function notation equals negative fourth degree root from 2 minus 2. So that looks like it's just negative 0, which is the same as 0. Okay, the value is 0. Let's go for lower numbers. For example, 1. So how much is f of 1? F of 1 is negative fourth degree root of 2 minus 1. Instead of x, we have 1. So 2 minus 1 is 1, and fourth degree root of 1 is 1, so altogether is negative 1. Here is our value, negative 1. Okay, now we can choose any number that we wish. Remember, the graph will go from 2 to the left. So we chose 2, we chose 1. Well, we can choose 0 or negative 1 or negative 5. That's up to us. Those values may not be exact, but we can use calculator and estimate. So if I choose x equals 0, f of 0 is equal negative fourth degree root of 2 minus 0. So it's the same as negative fourth degree root of 2. Let's check with the calculator how much is that. Negative 2 to the exponent 1/4. It turns out to be approximately negative 1.2 rounded to one place value. Okay, negative 1.2. And maybe let's check at the end of our grid, for example at negative 5. So f of negative 5 is negative fourth degree root from 2 minus negative 5. So we have two negatives, therefore it's 2 plus 5. That gives us negative fourth degree root of 7. And again estimate using calculator. Negative 7 to the exponent 1/4 approximately equals negative 1.6. Okay, let's record this, negative 1.6. Now we can plot all these points and see how the graph looks like. So 2, 0 is here, 1, negative 1, it's over there, 0, negative 1.2, it's approximately here, and negative 5, negative 1.6 looks like it's somewhere here. Okay, so it looks like these points need to be joined until 2, but not past the 2. 2 is the last point of our curve. Okay, let's join them. Here's our curve. And as before, let's mark the domain of our graph. Here's the domain from -infinity until 2. The range, the values of the graph, will be the y values, and those y values are below 0. So again, it will be from -infinity until 0. So as you see, the graph of this more complicated function, it's very similar in a shape to the graph of just regular fourth degree root of x. However, this shape looks like it's flipped over the x-axis, and it's flipped over the y-axis, and it is shifted as well. So we just learned some shapes of higher index radical functions.